This final video of Unit 3 Acceleration is just going to go over some practice problems. What I'm going to do is I'm going to go ahead and work through one practice problem thoroughly, and then for the other ones I'm going to go ahead and allow you to do them on your own and then hit play to resume. So let's go ahead and do this first one. It says a subway train in Washington, D.C. starts from rest and accelerates at 2 meters per second for 12 seconds. Notice it's very open-ended, doesn't really ask you a question, because the idea of this is I want you to be able to do everything we've learned so far in this class. That includes motion maps, qualitative graphing, and finally kinematic equations that would get us some additional information. So let's first start out with a motion map. All right, remember, you as the physicist can decide which direction you want your motion map. It's always habit for me to make the motion happen in the same direction that's positive. So that means to the right. Okay, so I'm going to go ahead and do velocity first. So velocity, I'm going to go ahead and make travel to the right, since that would make my velocities positive. And in this situation, I notice that the subway train is starting from rest and accelerating at 2 meters per second. And that should be 2 meters per second squared, excuse me, for 12 seconds. So it's speeding up. So what I'm going to do is I'm going to draw my arrow like this. 2, 3, 4, 5, 6, and then 7. We should have 12 for 12 seconds, but since I'm running out of space on the board, we'll go with that. Just to be safe, I'm going to draw some slashes here just to show that they are getting bigger. There we go. So I can see that my velocity is definitely increasing. Now, if my velocity is increasing and it's moving to the right, that also needs to be the same for my acceleration. Notice my acceleration arrows are all the same length because acceleration is always constant in this unit. There we go. All right, so that's my motion map. Let's go ahead now and look at our qualitative graphs. So I'm going to have position versus time. I'm going to have velocity versus time. And I'm going to have acceleration versus time. Okay, first of all, remember these are qualitative graphs, so we're not going to necessarily have numbers in them. We just want to know what their general shape is. So for position, it's moving away from the origin, speeding up. So that's going to have this shape right here. And that should be, at the origin. So let me redraw that a little bit better. There we go. My velocity graph, I'm moving away from the origin. So my away from the origin tells me it's going to be somewhere in this region up here. I just have to know, is it going towards 0 meters per second or is it going away from 0 meters per second? And since it's speeding up, I know it has to be going away. Finally, acceleration is just the slope of a velocity graph. Since the slope of the velocity graph is positive, that means my acceleration must be positive. And it's a flat horizontal line since acceleration is constant. Finally, let's go ahead and see what information we can solve for. What I like to do is I like to analyze the problem, meaning I write down the information that the problem gives me. So let's read through. A subway train car in Washington, D.C. starts from rest. That tells me that my initial velocity is 0 meters per second. It accelerates at 2 meters per second squared, so I know my acceleration. And my time, it tells me, is 12 seconds. Let's think of some other things we've seen already that we could maybe solve for. Well, I could potentially solve for change in x, which would be my displacement. And I could also solve for a final velocity. Okay, let's go ahead and do delta x first. Let's think about what we have, okay? We have an initial velocity, we have an acceleration, we have a time, and I want to find delta x. Well, there's two equations that I know have delta x in them. The first one is kinematic equation number 2, and the next one is kinematic equation number 3. But if I look at all my equations, I notice the one equation that has everything in there is this one. Okay? Notice I've got an initial velocity, I have a time, and I have an acceleration. So I could therefore solve for delta x. So delta x would be equal to Initial velocity is 0, which makes it really nice that whole thing goes away. So delta x will just equal 1/2. My acceleration is 2.0, and my time is 12, and don't forget to square the time. Now when I calculate that, I'm going to do 12 squared, which is 144, times 2, and then times 1/2, or 0.5. My delta x ends up being 144 meters. So that tells me that this subway car in 12 seconds has gone 144 meters. Finally, I want to solve for final velocity. There are two equations that I can use to solve for final velocity. Use whichever one you would like. I'm going to go ahead and use this one right here. V final equals V initial plus AT. My final velocity is what I'm solving for. I know initial, I know my acceleration, and I know my time. So V final equals, since initial velocity is 0, that just goes away. So final velocity is equal to the acceleration, which is 2, times the time, which is 12 seconds. Times those out, and my final velocity after 12 seconds will be 24 meters per second. So notice this problem is a good review of everything we've learned. Okay, what I'd like you to do right now is I would like you to pause the video and do all of the above that we just did, and then hit play to reveal the answer. Okay, let's go ahead and take a look at what I've got on the screen. First thing is the motion map. Notice the velocity vectors in blue are getting shorter because the car is coming to a stop. It's braking. If the car is slowing down and the velocity is in the positive direction, acceleration must be the opposite, or in the negative direction, to slow it down. If you look at the qualitative graphs that are on the left, notice the position versus time graph has an object that's moving away from the origin but slowing down. The velocity graph has the velocity drawn up in the positive region, but it's going down towards 0 meters per second since it is coming to a stop. And since the slope of the velocity graph is negative, that's why acceleration is negative or drawn below the axis. Finally, you'll see in the boxed area is my information that I know. I know the car is traveling at 15 meters per second initially. Its final must be 0 since it is stopping. And it went 25 meters in that stopping process. Two things that I can solve for are acceleration and time. What I'm going to do is I'm going to go ahead and pause the video again and allow you to try to figure out which kinematic equations to use, and then hit play to reveal the answers. Okay, notice for the first one that I'm using V final squared equals V initial squared plus 2a delta x. This is because I need to find acceleration first, but I don't have time. Notice how I plug in my values. 0 squared equals 15 squared plus 2a 25. I simplify that out by squaring my values and then timesing 2 and 25 together. And after I do some manipulation, I get my acceleration is negative 4.5 meters per second squared. This makes total sense because since my velocities are all positive and the object is slowing down, I have to have a negative acceleration. Knowing my acceleration now of negative 4.5, I can now use my other equation, V final equals V initial plus AT, plug in my values, and end up getting a time of 3.33 seconds. All right. Now this one I'm actually going to walk through with you because this one involves an object that is dropping, or in other words, it's under the acceleration of gravity. So the object here is a ball is dropped from a building that is 52 meters high. This is the first example you may have ever seen where an object is moving vertically rather than horizontally. The same rules are going to apply, we just need to shift a couple things. So for example, when I draw my motion map, I'm going to make my reference arrow vertical instead of horizontal. Now the ball is being dropped from the building. You have the option, as the physicist, here's the building. You can make your origin at the very top or the very bottom. If you make the origin at the top of the building, then that means you can make down positive. If you make the bottom of the building the origin, that means you'd make up positive. Well, if I'm dropping a ball and it's going to fall from the building, the object's moving down. And so it makes sense to make down positive, so that way all of my velocities are positive. So I'm going to erase this bottom reference arrow, and I'm going to make my reference arrow right at the top, just like this. So let's go ahead and draw in my velocity vectors first. My velocity vectors are going to start small, and it's going to speed up more and more and more until obviously it finally gets to the bottom of the building. Since the object is speeding up, and I've said down is positive, my acceleration vectors are also going to point down. There we go. So that is a motion map for a vertical situation. Notice it's the same concept, we just had to switch it around a little bit to be vertical to indicate with the problem. Now what I'm going to do is I'm going to go ahead and sketch what my three graphs would look like for position versus time, velocity versus time, and then acceleration versus time. Okay. The key thing is not to get freaked out at the fact that it's vertical instead of horizontal. Remember, it's still the same thing. Ask yourself, is the object moving towards the origin or away from the origin? The way we set it up, the object's moving away from the origin, since we made the top of the building the origin. And so since it's moving away from the origin and speeding up, the position graph is still going to look like this. The velocity is moving in the positive direction, since down is positive and that's which way the arrows are pointing. So that means that the velocity is going to be up here in the positive region, and since it's speeding up, it's going to look like that. And since the slope of my velocity graph is positive, that means my acceleration is going to be a positive straight horizontal line. Finally, let's write down some information that we know so we can solve for any other problems we need to. Okay, it doesn't seem like the problem's giving us a lot of information. In fact, the only thing you may be thinking is, well, I know the change in position is 52 meters. Notice that I put delta y instead of delta x just because we're dealing with vertical. It doesn't change the other three equations we've already gone through. It's just y because now we're dealing with vertical instead of horizontal. And you might be thinking, well, dang it, that's all I know. But you actually know more information than just that. Think about it. If you're dropping a ball from the building, what was its initial velocity? Well, if you're just dropping it, the initial velocity must have been 0. You dropped it from rest. And even though it doesn't explicitly state it, what is accelerating the ball? Well, the only thing accelerating the ball is gravity. And we know what the acceleration of gravity is. It's 10 meters per second squared. Now, take a moment and stop and ask yourself, is it negative 10 or is it positive 10? Notice, since we made down positive and acceleration is pointing down, then it must be positive 10 meters per second squared. So, now that we have that information, we could solve for what final velocity is. And we could solve for how much time it's in the air for before it hits the ground. Let's do final velocity first. Now, some students are tempted to think, well, wait a minute, isn't final velocity just 0? After all, it hits the ground. Doesn't it just come to rest? When the problem states what is the final velocity, it's saying what's the final velocity the instant before it hits the ground. Because once the ball hits the ground, then we're dealing with a whole other host of situations and questions for physics. We just want to know when the object is in the air, right before it hits the ground, what's the final velocity. The equation I'm going to use to solve for final velocity, since all I know is the displacement and the acceleration, is v final squared equals v initial squared plus 2a delta y instead of delta x. I'm using this equation since I don't know time. All right, final velocity is what I'm solving for. My initial velocity is 0 plus 2 times the acceleration of gravity is 10 times the height of the building, which is 52 meters. When I multiply all that out, v final squared equals approximately 1,040. And if I square root both of those, I'll end up getting my final velocity. And let's see here. Final velocity is approximately 32.25 meters per second. So that is the velocity it would reach right before it hits the ground. The last thing I'd want to solve for now is time. There's two equations that have time in it, but I'm going to use the easier of the two. I'm going to just use Flava Flav, which is V final equals V initial plus AT. Alright, I know what my final velocity is. It's 32.25. My initial velocity was 0, plus my acceleration is 10, and I want to solve for time. Doing that, I'm going to end up getting a time of approximately 3.22 seconds. Now, what I'm going to do real quickly is I'm just going to erase that last problem, and I'm going to show you how you can do the exact same thing using the other equation that has time in it. So I'm going to erase this, and instead of using that equation, I'm going to use this equation. Delta y, notice it's y instead of x because it's vertical, is equal to v initial t plus 1/2 at squared. This equation is really easy to use because my initial velocity is 0, meaning this term goes away. So that ends up being 52 meters, which is the delta y, is equal to 1/2 10 t squared. If I do 52 divided by 1/2, I get 26. If I divide that by 10, I get 2.6 equals t squared. And if I square root both sides, I'm going to end up getting, whoops, excuse me, that was a mistake there. If I do 52 divided by 1/2, I get 104. Divide that by 10, I get 10.4. That's equal to t squared. That looks more like it. Then I'd square root that answer, and I'd end up getting time is also equal to 3.22 seconds. So you can see sometimes there's multiple ways to do a problem. Both will get you the same answer. All right, last one. This last one, I'd like you to pause the video and do what you can on your own, and then go ahead and hit play to reveal any answers. Okay, let's go ahead and now look at this problem. You'll notice I only have the motion map and the graphs because I wanted to walk through a couple things. First of all, we have the situation. A ball is thrown upward with a speed of 7 meters per second. So you're throwing it out of your hand. It has an initial speed of 7 meters per second. From your experience, hopefully you realize that when you throw an object in the air, eventually it reaches a point to where it's going to stop. So notice first of all my reference arrow on the left. My reference arrow, I make the origin at the very bottom. The origin is kind of like where your hand is. So as soon as the object leaves your hand, that would be your origin. And then I'm making up positive since that's where the object's moving. So my velocity is positive since it's going up, but notice what's happening is it's slowing down. So that means that I'm going to make my position graph over here, that curve that kind of levels out. Now, it's moving away from the origin, so that means the velocity is up here in the positive region, but it is indeed slowing down. Finally, I've got my acceleration is going to be the slope of your velocity graph. Since the velocity graph is negative, that's why the acceleration is a negative line right down here at the bottom. All right, now notice what the acceleration is doing on my motion map. Since the object is slowing down, and the velocity vectors are pointing up, the acceleration arrows or acceleration vectors have to be pointing down. And the acceleration is being caused by gravity. Now, what we're going to do is we're going to analyze the second part of motion. All right. Now, I only did the first part of the motion, which was the ball going up. You may have also chose to finish out the motion and say, well, whatever goes up must come down. So let's go ahead and look at that situation if you were to do the whole range of motion. So we already have the first half where the object or the ball is being thrown up and stopping at the very height. Remember though, it has to come back down. So that means my velocity vector motion map would just continue and it would speed up as it was going down. After all, doesn't that make sense? An object speeds up with gravity pulling it towards the earth. So my full velocity motion map would look like that. Notice that it's slowing down on the way up, and then it's speeding up on the way down. Also, and we'll learn this on later on in Unit 4, but notice that the magnitude of the arrows is equal on the way down. If we're assuming no air resistance or negligible air resistance, then it must be the same speed on the way down as it was going up. Now, you may be asking, well, what are the acceleration vectors? The acceleration vectors are still going to point down. After all, gravity doesn't reverse its direction and all of a sudden point up. Gravity is always pointing down towards the Earth. So the acceleration vectors would be still pointing down even on the trip back. And think about it, that makes total sense. Because look at acceleration. Acceleration is always pointing down, right? And I've said up is positive. So what would that mean the sign of acceleration is? Well, it's always negative. It was negative here and it was negative here. And so we can show that by continuing to draw our line. And I'm going to separate the motion by dotted lines so you can see the first half is for on the way up and the second half is for on the way down. So acceleration is negative always. But let's look at velocity. Velocity was positive on the way up because the velocity vectors are pointing up, and that's what direction positive is. But on the way back down, it was negative since they were pointing the opposite direction. And so to draw my velocity graph, my velocity for this on the way down is going to be drawn in the down region of velocity, and it's speeding up. So it's going to look something like this. And notice that makes perfect sense. When velocity was positive and acceleration was negative, what was it doing? Slowing down. Now that the the velocity is negative and the acceleration is still negative, since they have the same sign, they will be speeding up. Let's finish it out by drawing our position graph. Our position graph was originally curving down in the beginning to show that it was moving away from the origin, slowing down. But now, on the way back, it's moving back towards the origin, speeding up. So it creates a bell curve just like that. So this would be the full motion of the ball being thrown upward and then coming back down towards the origin. Now, you may be sitting here thinking, wow, that's really confusing, or that's a lot to think about. But really, if you just think about it for a moment using our everyday life situations and experiences, that makes total sense. And if we stop and just look at the graphs individually and separately, we can see how that makes perfect sense physics-wise. Now what we're going to do is we're going to solve the problem. We're going to write down the information that we've been given, and we're going to go ahead and see if we can use some kinematic equations in order to figure out some information. So what do we know about this ball? Well, we know that its initial velocity is 7 meters per second. And notice it's positive 7 meters per second, since that was actually the direction it was pointing. It was pointing up. What are some other things that we know? Well, we're dealing with a ball that's being thrown up in the air, or it's on free fall. So what that means is the acceleration is going to be the acceleration due to gravity, which we know is 10. Now the question is it positive 10 meters per second squared, or is it negative 10 meters per second squared? Well, we have to look at the motion map. Notice all the motion map vector arrows for acceleration right here, they're all pointing down. And since I made up positive, that means acceleration in this example must be negative. So you always have to look in every single problem whether or not it's positive or negative based on your motion map. All right, what else are some things that we know? Well, final velocity. Now this one's a tricky one, okay? I'm going to analyze this problem just using the first half of motion, meaning I'm just going to analyze the problem just going to the top of its peak. That's it. So if it's just going to the top of its peak, which is right here, what's its final velocity? The answer is 0. Okay. Now, what are some things we could solve for? The first thing we could solve for is we could say, how much time does it take to get to the top of the peak? Finally, we could figure out how high does it go, or what is its delta y. Okay, let's solve for time first. Since I have an initial velocity, a final velocity, and an acceleration, I'm going to use this equation right here to figure out time. My final velocity at the top of the peak is 0. The initial velocity that it was thrown up with is 7 meters per second. Plus, my acceleration is negative 10, and t is what I'm solving for. If I move the 7 onto the other side, I get negative 7 equals negative 10 t. And dividing both sides by negative 10 gives me a time of 0.7 seconds. Now notice, what if you hadn't made the 10 negative, but what if you left the 10 positive? Well, then you would have gotten a negative 7 divided by a positive 10, and you would have ended up getting a negative 0.7 seconds, which you know that's not possible. So that is another kind of check to make sure that you make your acceleration have the right sign, and in this problem it's negative. Alright, so now I know my time is 0.7 seconds. The final thing I'm going to figure out is I'm going to figure out how high did the ball go. So I'm going to erase my work so I've got some space here. There we go. And I'm going to solve for delta y. Now there's two equations that have delta y in it. It doesn't matter which one you use because you have all the information. I'm going to go ahead and use this one right here. V final squared equals V initial squared plus 2a delta y. My final velocity is 0 since it reaches the top. My initial velocity was the 7 plus 2 times the acceleration, make sure it's negative 10, times delta y. And delta y is what I'm solving for. 0 squared is just going to be 0. 7 squared is going to be 49. And then 2 times a negative 10 gives us a negative 20, and then delta y. Moving the 49 onto the left side gives me negative 49 equals negative 20 delta y. And dividing both sides by negative 20 gives me my answer of 2.45 meters. That's how high up it went. Now, to show you how you also could have got the problem right using the other equation, I'm going to do that now. I'm going to leave the answer of 2.45, but I'm going to erase the work and show you the second equation that you could have used. We could have also used this equation right here. Delta y equals v initial t plus 1/2 at squared. Delta y is what I'm solving for. My initial velocity was 7. The time it takes is 0.7 seconds. Plus 1/2, my acceleration is negative 10. My time is 0.7, and don't forget to square it. That makes delta y equals 7 times 0.7 is going to give me 4.9, plus 1/2 times negative 10 is going to be negative 5, times 0.7 squared. That's going to give me a negative 2.45. Add those together, and I end up getting a delta y also equals 2.45 meters. So once again, there's multiple options that you can use. The general rule of thumb is the more information that you know, the more equations you have at your disposal to use. This concludes the video on kinematic equations and extra practice.